Hello, everybody. Did you all have a chance to check out the space below? How did you like it? So, hold on. So, uh, welcome to Dolby Soho. So in Dolby, we believe in advancing the science of sight and sound to create and enable spectacular experiences. And what I really like about this space is it exemplifies what we do, where science meets art and technology meets imagination. This is our corporate headquarters in San Francisco, where we work. It's a 16-story building in the heart of San Francisco. Amazing views, but what I'm most proud of is this has over 100 labs and listening rooms, which kind of pays attention to how seriously we take audio research. And our largest lab is a 250-seat Dolby Cinema Theater with the world's best audio and video experience. So the thing I would like to very much talk about is a state of the art in deep learning for audio. Here we stand in 2019, really at the height of some of the greatest accomplishments which have happened. But I feel this is also the beginning, and it's up to us where the technology takes us. And before I go on to the future, I would like to kind of take a step back and see how we got here. So deep learning has a long history, starting with the perceptron in 1950s. We all know this. Over the next 50 years, a lot of work was done. But I feel there was a defining moment in 2012 when Alex Krashinsky won the ImageNet competition by a huge margin, which triggered a boom in the use of deep learning in the industry. And what made deep learning impactful with AlexNet was that he was working with raw pixels without any handcrafted features. And I think that worked very well. And personally, that is what inspired me to get into deep learning is back in 2013, Andrew Ng gave a lecture in Stanford where he described with deep learning, how with deep learning we could use unsupervised feature learning. He talked about challenges with feature extraction, how hard it is, how time-consuming it is, and how with deep learning we can get rid of all of that. And it implied to a lot of people that with deep learning, we don't need any domain expertise. But if you look, convolutional neural networks itself were inspired by how we understand our visual processing. So this is what the ultimate dream was, that we just give input, give it to a deep learning algorithm, and we get output. So again, if you go back to 50s, we got experiments by Hubel and Wiesel, which gave us understanding of how the visual cortex system worked and the hierarchical organization in early visual pathways, which inspired neocognitrons, which inspired Jan LeCun to create LeNets. So even if we don't use feature learning in vision tasks, the architecture, CNNs itself, are based on understanding of visual cortex. So if you think about it, the domain knowledge is embedded in the architecture itself. And in the audio task, switching to raw audio was a bit more challenging. It proved to be a little bit more challenging than that. We still use spectrogram and feed the spectrogram into image-based CNN when we are working with, say, wake word detection. And we continue to use spectrogram and CNN for tasks like scene classification, language detection. And these are a few recent papers which have been accepted to ICASP. So more fundamentally, the question we need to ask ourselves is who we are. What do we think of ourselves? And don't get me wrong, there are excellent reasons for using CNNs. For one, they work really well. If you want state-of-the-art results, you need to use CNNs. But I also feel for breakthroughs in this field, we need to part ways with our perspectives, which are inherently visual, and start to feed audio knowledge into the architecture itself. And when we understand audio, we need to start using audio to build better architectures. And interestingly, a lot of work and a lot of brilliant work has been done in this field. In 2016, we had multi-scale convolution front ends, which used trainable filters as a first layer. In 2017, Jordi published a paper which won the ISMER's Best Student Award, showing that if there is enough data, waveform-based models can get better results than spectrogram-based models. And in 2018, WaveUnit adopted units to time domain, enabling end-to-end source separation in time domain. And also in 2018, Mirco from MILA, who's here with us today, built a waveform front end using parameterized sync function. And this is not a comprehensive list, just some of a few papers I am aware of on the classification side. And if we switch to the generation side, a lot of sample-based papers appeared in 2016 as well. WaveNet, which used dilated convolution, and SampleRNN, which used multi-rate RNN operating at different resolution. The interesting part, which I like with both these papers, is they both account for the temporal dependency of audio, or the temporal nature of audio, and the high resolution short-term dependency and the low resolution long-term dependency audio tends to have. And in my mind, these papers were so powerful, and the learnings we had from these were so powerful that they spawned a breakthrough in speech encoding. In the last few years, both Google and Dolby have published work which drastically improves speech coding. Google published a paper on low bit rate, and they have subsequently published several papers. And we focused on high quality speech. And in both these cases, we have been able to reduce the bit rate by a factor of 2.5x to 8x. And just to give you an idea how significant this is, the last time we had a significant breakthrough in speech coding was in 1984, with KELP came out. And at that time, the improvement was approximately 20 to 30%. This is the biggest breakthrough speech coding has ever seen. And Zhou will be covering a little bit more of will be giving more details of the work we have been doing in this area. So, like I said, we have been using our understanding of audio to build better features. Can we instead use our knowledge to design networks which are more suitable for audio? And I believe it's up to us to define where this incredible technology takes us. So with that, here is the agenda for today. We have a great panel of speakers who will be presenting some of their latest research and giving an overview of the application deep learning for audio is enabling. A lot of exciting talks and a lot of exciting presentations. Each presentation is 20 minutes long. Most speakers will have time for questions at the very end. They have been asked to present for 15 minutes and leave 5 minutes for Q&A. We'll have a break of 30 minutes. If you want to use the restroom in the break, the restroom is in the basement, and you'll have to use the elevator. So we did have a 30-minute break exactly for that reason. Any questions before I hand it over to Mirco? Thank you. So Mirco is doing his postdoc at MILA under Professor Yoshua Bengio with a focus on deep learning applications like speech and speaker recognition, robust acoustic scene analysis, and cooperative learning and unsupervised learning. He has authored over 40 papers, and he will be presenting his work on processing raw audio with SincNet. Mirco.
Thank you very much. Let me go back. Okay. Thank you very much for inviting me. And today I'm going to talk about one of my recent works, which is about an architecture that we have developed for processing raw audio directly. When we process raw audio directly, we have to consider that speech is a kind of nasty signal, right? Because speech is very high dimensional. And we all know from the machine learning perspective how difficult it is to deal with such very high dimensional data. Just to give you an example, if we have the standard sampling frequency of 16 kilohertz, we may have 16,000 samples per second, which is really a lot. For this reason, still, we employ a lot this kind of handcrafted computer handcrafted features like MFCC or filter banks that allow us to make the signal more compact. And let me first of all say that these are very good representations because humans use their knowledge to handcraft this representation. And mainly, these representations are derived from a perceptual evidence, which is totally fine. But this doesn't necessarily mean that these features are good for all the applications. And here I try to give you a very simple example. So if we take the spectrum of this vowel, we have a lot of narrowband peaks that corresponds to the pitch or to the formants of the vowel. But if we process our audio data, this vowel with the MARL filter bank, we may have this kind of we basically smooth the spectrum, and we may hinder the extraction of very important features of the speech signal like pitch, formants, and etc. So to avoid this problem in the community, there is a growing popularity towards CNN convolutional neural networks that are directly fed by the raw samples directly. So typically, this is the architecture that it is used. We just put in input in the waveform, and we have in output some kind of prediction over speaker, over phonemes, or whatever we want. In my opinion, the most critical part of this architecture is the first convolutional layer. Why? Because first of all, the convolutional neural layer is the layer that has to deal with such a high dimensionality. But also, the first hidden layer is very far away from the cost function and may suffer more from problems like vanishing gradient, which are very critical in deep learning. So if you try to train a neural network on raw sample directly on a speaker identification task or a speech recognition task, you may have something like that. So these are the filters. The first row here is the time dimension, and here is the frequency of the frequency representation of the filter. And you may learn filters which are kind of good, like this middle one, very selective in frequency. And there are also some filters that really kind of are difficult to understand why we learn something like that, right? Here we have a very noisy shape. Here we have, a kind of very weird multi-band shapes. So, yeah, these are the filters that you may find that are weird. And the main problem is that these filters are not only are bad because do not appeal to human intuition, but in my opinion, more than an interpretability issue here, it's a symptom that we are not learning an efficient representation. So when I saw something like that, I asked myself, how can help the neural network learning more meaningful filters? And usually, when you would like to help your neural network, the trick is to add a kind of prior knowledge. So this is a simple idea, is why don't we add prior knowledge in the input layer of the convolutional neural networks? So here is how a standard CNN works. So basically, you perform a convolution with the input signal with a set of FIR filters, finite impulse response filter, and we learn all the basic elements, all the basic tap of each filter, right? In SincNet, instead, we perform a convolution with a predefined kernel which only depends on few parameters. And we learn only few parameters. So the question can be now, okay, but what could be a good choice for this kernel? One reasonable choice, not necessarily the only one, is to implement a rectangular bandpass filter where instead of learning all the elements of the filter, we just learn the cutoff frequency. This can be simply done in this way. You can see the filters in the frequency domain can be seen as the difference between two low-pass filters with f2 greater than f1, and if you take the inverse Fourier transform on that, you may have this simple expression where you have to convolve your signal with a kernel that is based on the difference between two sinc functions oscillating at a different frequency. So if you use something like that, your filters become something like this, right? So you force them to have this rectangular shape, right? What are the properties of this simple model? First of all, we have few parameters. So if f is the number of filter and L is the length of each filter in the first convolutional layer, in a standard CNN, we have f times s L parameters, while in SincNet, we have just 2 times f, which is typically order of magnitude less. The other interesting aspect is that, as you can see, the number of parameters does not depend on the length of the filter. And this means that we can employ very long filters that can be very selective in the frequency domain without wasting parameters. So we have a better chance to learn this very narrow band information within the speech signal. One other property of the model is that we have a faster convergence to a better performance. Here is speaker identification, and you can see that SincNet converges faster and better. Faster because we have just few parameters to tune instead of tuning all the elements of the filters. Another good issue, good property is the interpretability. Here we have computed the cumulative frequency response of the filters. Means that we sum up all the filters just to see which are the area of the spectrums which are more covered by filter and which are the area less covered by filters. And if you take a look here into a convolutional neural network, you can see that the convolutional neural network focus on basically on the lower part of the spectrum. That totally makes sense because most of the energy of the speech signal is there. But with SincNet, you can see even something more because you can see clearly 3 peaks that likely corresponds to the average pitch formants, first formant and second formant. So you have better insights from the filters here. Sorry? The formant? The formant is the resonance of your vocal tract. So it's very important for speaker identification. It's also, we also have better interpretability. In speech recognition, here we artificially add noise into a specific bandwidth, where this bandwidth is not useful, of course. At the end of training, both CNN and SincNet are able to understand that they have to avoid this bandwidth. Look at here, this hole here correspond to the frequency of the noise here. But what is interesting is that SincNet learns it faster. So here is a standard CNN, and here is SincNet, where SincNet is able to learn that has to avoid this bandwidth just processing 1 single hour of speech. So it's very fast. Here are some results. So you may take a read to the paper for full results and so on. Here we have the speaker identification performance on TMIT and on LibreSpeech. And you can see that SincNet is better than a standard CNN fed by raw samples, and you are also better than more standard signal representations like filter banks and MFCC. While here on the other side, you can see the performance we have for speaker verification, which is an open set, more challenging than the closed set speaker identification before. This is able to outperform iVectors, and if you take a look into my recent papers, there are also results on Voxel Lab where we highlight the benefits of this approach in a more realistic speaker identification, speaker verification task. We also have tried SincNet on speech recognition. Here we have tried as a toy task, we have tried TMIT, which is phoneme recognition. And also we have tried DIRA, which is a data set characterized by a lot of noise and a lot of reverberation. And here TMIT is phoneme error rate, and DIRA is word error rate. And what is interesting here is that SincNet still outperforms standard CNN, also in noisy conditions. This is a very interesting result because I remember I was at a speech conference, was 2014, I guess, and there was a common belief that it was not possible to learn from scratch if you have reverberated and noisy data. I mean, learning from the raw samples directly. And this result shows that it's actually possible. And the trick is very simple. Just add meaningful prior knowledge and you are done. If I have 1 minute more, I can say that SincNet is a very simple technique. And we have many ideas now to improve it, and etc. And we have used SincNet in many applications. Here is my latest paper that I have just submitted to Interspeech, and we have used SincNet, as you can see here, to develop a kind of universal speech encoder that is able that is learned in an unsupervised way and is able to learn general features useful for many tasks like speech recognition, speaker identification, and so on. We also have tried SincNet on an end-to-end spoken language understanding, which is one step forward over standard speech recognition, and we have good results with that. So I'm okay with the time.
You have 4 minutes.
I have 4 minutes?
Yes.
So I prefer to take this time answering questions. And
so if you have any questions, let me know. I can pass the mic to you.
Thank you for the talk, Mirco. Could you tell us a little bit about the bandwidths of the learned wavelets, or whatever you call those basis functions? You've shown that they cover pretty much the whole bandwidth of speech, but what about the width of the band that the neural net learns? Is it sort of uniform or proportional to the center frequency, or all over the place?
Well, what we learn is the two cutoff frequency, F2 and F1. So the bandwidth is the difference between F2 and F1. And we have seen that this aspect is very task dependent. So in speech recognition, you try to use a larger bandwidth because in speech recognition, some phonemes like fricatives, like S or something, have a very large band. So you are trying to use all the band you have. While for speaker identification, you try to use just a narrow band. You focus on the lower part of the spectrum because is there the most important information. And I think this is one advantage of SincNet because you are really tuned on the task that you would like to address.
Thanks for your talk. Amazing work. So basically your SincNet is more or less a MAR wavelet, right? So it's a Mexican hat, one-dimensional Mexican hat. So I'm just wondering if you'd considered, sort of imaginary, a real valued, imaginary complex valued sort of wavelet, a classic Morley wavelet, to in effect capture phase, because at the moment you're only really capturing the magnitude of the signal. And so if you've done any work on that side of things, and a follow-up question is on that basis, had you considered, matching pursuit models, which is where effectively you're tuning the different basis functions across without necessarily a singular mother function that you're attempting to simply scale and translate?
Well, thank you for the question. In these weeks, these months, we are trying to improve SincNet in different ways. This is just the simple idea we had, but for instance, we are trying to combine SincNet with quaternion neural networks. So I have done, which are hypercomplex number. I'm collaborating with people from Avignon, France, on this project because they have seen good performance in a standard using quaternion neural networks. I have seen good performance using SincNet, and now we are trying to combine together. So this goes a little bit in the direction you suggested. And the other question was about the mother function, right?
Yeah, the mother function of the idea that in matching pursuit, you may not have a single function, but you actually have multiple bases.
Yeah. This is another idea that we don't have explored. We prefer to put it in a very simple way, but you can, if you want, add a kind of discrete number of functions that you can tune. And actually, during when I developed this technique, we have tried also different function than the SincNet for that implements the rectangular filters. We have tried triangular filters like the MAL ones, but at the end we have seen that this simple solution works decently well.
Any other questions? Last question.
Hey, sorry. So one thing that strikes me about this is because you're sort of learning so few parameters, I'm wondering, I don't know if you've explored this at all, even slightly, but in analogous to in computer vision, how you have adversarial examples, do you think that SincNet, because it's a simpler, or because you're sort of reducing that feature space so quickly, that it might be more robust to adversarial examples?
That's a good idea. I never thought about that, honestly, but it's something we may consider. I think that adversarial examples are well connected to high dimensional spaces. So it's possible that if we reduce the dimensionality a bit with SincNet, stuff are gonna be better. But adversarial examples are a problem even if you use standard features like FBank, which are very low dimension. So I'm not sure that this is gonna solve the problem, but I never check. Thank you.
Thank you so much, Mirco. So I would like to introduce Rachel. She's our next speaker. She's a research scientist at Spotify and recently completed her PhD under Professor Yuan Bello. Her research interests are at the intersection of audio signal processing and machine learning applied to musical audio. She will be presenting her work on units for vocal source separation. Rachel.
Hey everyone, thanks for the introduction. So today, as you said, I'm going to be talking about units for vocal source separation. So in a broad sense, what is the problem we're talking about? So vocal source separation is the problem of taking an audio signal and, for example, removing. No. Dead clicker. What do I do? Sorry, Google Slides. removing the voice, or isolating the voice. So this has been a problem that people have worked on for a long time. And for a long time, it was viewed as one of the hardest problems in audio signal processing, I would say. But around 2015, there started to be a breakthrough, enough that the press actually picked it up and said, oh, it's been a uniquely human ability, but now we can do it. I would say it was not solved yet at this point, but people started paying attention. So the classic way that people approached this problem that was working for a long time was based on non-negative matrix factorization. So this was taking the spectrogram of the mixture audio and decomposing it as a product of two non-negative matrices, one of a basis of spectral patterns and one of activations that you would learn. And this method took us a long way, and it's mathematically satisfying, it's intuitive, and you can tailor your solution to specific problems. So if you have a single speaker you want to separate, you can make your basis matrix tailored to that speaker, and it works well. But the problem is, if you want to generalize to many different singers, for example, you need a huge basis matrix, and the bigger the basis matrix, the more complex the solution, the slower it runs. So for this reason, people started to move away from NMF and move towards deep learning, also with the introduction of more data for this problem. So one of the earlier papers that was using deep learning for vocal source separation in music was called Deep Karaoke, good name. And it was a fully connected neural network, and they treated the problem as take the input mixture spectrogram and predict the separated vocal spectrogram and the separated accompaniment. And this was actually the paper that started generating press. But actually, this paper didn't quite reach the performance of the good NMF-based models. But around 2017, we started getting really good sounding models. So according to one evaluation campaign, the MIRX campaign, the best model was based on the Chimera model. And this is basically a bidirectional LSTM model. And similarly, according to a different evaluation campaign on different data, another bidirectional LSTM model was the best model. And the nice thing about bidirectional LSTMs is we're working with temporal data, so it's good at modeling those differences. So what did we do? So the work that I'm going to be presenting now was led by my colleague Andreas Janssen and is presented in this ISMIR paper, if you want to read more details. So first, if you look at the publicly available data for this problem, you basically have 3 data sets, and they're relatively small as deep learning goes. So you have DSD100 and MedleyDB, which have a total of 170 professional quality tracks. And then you have iCala, which is 252 30-second karaoke clips. You have the left channel with the singer and the right channel with the accompaniment, but they're more artificial. So this wasn't really enough for our purposes, so we wanted to instead mine the Spotify catalog. So it turns out that a lot of artists release instrumental versions of their music. And that's, it turns out that you can mine the catalog for pairs of mixtures and their instrumentals. So we queried our catalog for music with the same artist, the same duration, and the same title plus or minus the word instrumental. And this ends up giving you a pair of 20,000 pairs of commercial music. The one caveat with this is these are not perfect pairs, right? So they're potentially having different mastering, slightly different EQs. So when you pair them, you're not getting a perfect version of the instrumental. And if you just subtract the mixture and the instrumental, you don't get a perfect vocal signal. You get a kind of noisy vocal signal. But we work with this anyway. And the genre distribution of this is concentrated around pop and rap, but you also have a pretty good distribution over a variety of genres. So for our model, the input representation we used was just a spectrogram, and we split it into time patches of 128 frames to train the model. We do this for the mixture, the instrumental, and the vocals. Then we frame the learning problem as learning a mask. So we want to learn a matrix, which we call a mask, which when multiplied pointwise with the mixture magnitude gives you something that is close to the magnitude of the source. So how do we learn this mask? So, we use a unit architecture, which was inspired from image recognition, as we always do. So the unit architecture is an encoder-decoder convolutional model, and it's got skip connections. So the decoder layers in addition to having the previous decoder features as input, they also have the corresponding encoder features as input. And this allows the model to better model higher density, higher frequency information. So when we wrote this paper, people weren't really using UNets for audio yet. So we were inspired by the pix-to-pix model, which was translating related types of images. So for example, going from a satellite image of a map to, oh, you can't see it at all, but a Google Map style version of the map, or a black and white version to a color version. So it's actually quite similar to our problem where we have a mixture spectrogram and we want to kind of erase some information from it. So once we've learned this mask, we convert back to audio by inverting the STFT, but to invert the STFT you need phase, and in this initial work we use the phase of the mixture. So before I talk about results, I'm going to show you some examples. Hopefully they work. Can you adjust the EQ or something? This should be the vocals. The instrumentals. Okay, so it wasn't actually showing you exactly what it was, because you heard in the mixture, you couldn't really hear the vocals. At least I couldn't from here. Maybe you guys could. Let's. Yeah, it was weird. Okay, let's see if the next one sounds better. Okay, so you get a slightly better example there. I promise the quality is actually better than what you're hearing right now. And the last example, this is where it starts to fail a little bit, is on the weirder vocal style. So this is Metallica. You can change the slide. This goes in a loop otherwise. So you probably heard that the quality of the instrumentals in general is much higher than the quality of the vocals. So you can pretty well erase the vocals, but the vocal signal is kind of phasey and weird. So to quantitatively evaluate this, first at the skip connections. So just for audio, we wanted to see if the presence of these skip connections in the UNet actually helps. So first, just inspecting the learned masks for this one example, you can see that the mask from a UNet versus the baseline where we train the same model without skip connections, the baseline is much blurrier, essentially, right? It's not capturing the higher resolution information, where the UNet is giving you a better mask. And so we evaluate our UNet model, our baseline model, and the Chimera network, the previous state of the art, using the typical source separation metrics. And in layman's terms, these basically measure how much the source is distorted, how well the background is removed, and how much were artifacts introduced. So we evaluated our model on the iCala data set, and each segment in between lines is a different metric. It's kind of hard to see. And this yellow dot indicates the UNet performance. So you can see for basically all the metrics and vocals and instrumentals, we're getting a significant bump above the baseline. So the skip connections help a lot. And we're getting, most cases, a boost above the Chimera network. But it's been shown that these metrics are not necessarily well correlated with human perception. So we can show that we have better quantitative metrics, but that doesn't mean that people will actually say that they're better. So we also complemented our evaluation with an offline study, or an offline perceptual study. So for the vocals and the background music, we asked listeners to tell us how well the isolated audio sounded by itself, so how is the quality of the audio, and we also asked them to measure how well we removed the background source. And we got 99 respondents and around 1,500 total responses. And we used Crowdflower to do our evaluation, and we gave them randomized examples, and we asked them to rate on a Likert scale of 1 to 7 how good the quality was. And for vocals on 2 data sets, MedleyDB and ICALA, we see a small bump between the UNet and the previous baselines, but a small but significant bump. But on instrumentals, it's actually a quite big bump. And people could really consistently hear the difference and thought that the UNet sounded better. So since this paper came out, we've noticed in the music and speech domain like a trend of people starting to use UNets a lot more. And in our paper, we didn't really motivate the use of the UNet, but it seems to be working well in general, and so people have started asking more, well, why is this working well? But we've seen it for source separation problems in music and in speech, and for other music-related problems like melody extraction. And shortly after this work was done, Daniel Soler, who was presented in one of the previous talks, did a waveform version of this model, which worked even better. So we brought him as our intern. So on this note, I'd like to thank you for your attention, and I'll take questions.
Thank you so much, Rachel.
Thank you for the talk, Rachel. Do you have any special handling of stereo information? Are you using like a fully convolutional 3D model, or you just run track by channel by channel?
So in this particular work, we were using mono audio. But in later iterations, we were using stereo, and it helps quite a lot, actually, because especially if you have panning information, yeah, it makes a big difference. So we just treat it as an extra channel on the input and output.
Hi. Before, when you make us listen to those kind of clips, I could hear a lot of high-pitched noise. Is it for just the recording, or is actually the results of actually the model?
So you should have, the first piece you should have heard was the original song. So if you heard high-frequency information, it's just part of the something in the
system. Oh,
yeah.
okay, I see.
But yeah, in general, like you don't get high-frequency artifacts. You get the biggest artifacts you get are phase and then some interference from the background, because we're using the mixer phase.
Gotcha. Thanks.
Just a curiosity. It's about the importance of the phase in this kind of task, right? So you just inject the phase of the mixture. Just wondering if you try to inject other kind of, for instance, the real phase or something, what happens?
Yeah, so if you use the real phase, of course, it sounds better. But actually for vocals in particular, I think you can get away a lot with using the mixture phase, because the vocals they tend to be the louder source, which means the phase is the most dominant. So you're masking out every other source, so you're actually getting something pretty close to the ideal phase, actually. It's not true for other instruments.
Have you also tried to use something Griffin-Lehm after to reconstruct back the...
Yeah. It works worse. In general, it's way better to use the mixture phase than to try to reconstruct, at least so far. At least everything I've seen.
Thank you.
Hey, nice talk, thank you. I was just wondering about the size of the audio sample that's going into the UNet, and about the potential application for UNets to kind of real-time audio processing. Can you speak to that a little bit?
Sure, so I have to remember the math, but it's, I think, around a half-second input. I'm not actually sure, I have to check, but it's something around there. And yeah, it's a fully convolutional network, so it should, there's nothing stopping it from being real-time. We haven't explored that direction, but it should definitely be possible.
Any other questions? Thank you so much. Yeah. No, we have time. We have time.
Just a quick question. You mentioned the instrumental and vocal versions of the tracks, and sorry, I might have missed it. Did you like filter out the ones where the instrumental was a little bit different, or
No.
did you actually have your networks try to predict that slightly different instrumental track and kind of do automatic EQing or filtering?
Yeah, it's kind of noise in the model, let's say. So actually, I didn't talk about it, but we actually trained two separate models, one predicting instrumentals and one predicting vocals, rather than doing one predicting instrumentals and residual. The residual ends up being kind of garbage. It's weird, but it's better to model the vocals directly because we don't have a perfect linear combination. Yeah.
Questions? Cool. Thank you so much, Rachel.
Thank you. Yeah, so thank you for the introduction. I'm Scott. I am a research scientist at Google in Cambridge. And I first wanted to acknowledge my teammates and collaborators at Google. They're all co-authors on this work. We're spread out between Cambridge and Mountain View and Seattle and San Francisco. Here is a overview of my talk. So first I just want to talk about the basic architecture of modern audio separation systems. Then I want to talk about two recent advances that we have been working on and that we have found really improve speech enhancement performance. And then finally, I'm going to stretch the scope of my abstract a little bit and talk about some brand new stuff that we've been working on that we're actually pretty excited about on universal source separation, if you will allow me. So as we've seen in the last talk, state-of-the-art sound separation systems generally rely on masking-based architectures. And so the basic idea here is that, let me see if this works. I saw a cool pointer earlier. Okay, maybe it doesn't work. So we have some mixture audio that's coming in. We're going to consider the single microphone case throughout this talk. At that microphone, we're observing some mixture of speech and noise. And so what we usually do is we create some features using an analysis basis. Usually this has been the short time Fourier transform. These get fed to a deep network. One of our more successful architectures lately has been a two-dimensional CNN going into a bidirectional LSTM followed by some dense layers. And this network produces a mask. And this is a matrix that we element-wise multiply with our analysis basis. And then we run those mask coefficients through a synthesis transform, which is often the inverse short time Fourier transform. And hopefully, if everything goes right, we get separated sources at the output. And if we're doing speech enhancement, we really only care about this speech source, which is going to be hopefully clean speech. The loss function that we've actually adopted these days to train these networks is actually in the time domain. In the past, it was very popular to use losses on the spectrogram itself. So you'd use like an L2 loss on the masked STFT, and that's how you train your network. But we've started to observe better results by actually training with this time domain loss. And this is actually a negative SNR, a negative signal to noise ratio. And the interesting thing about this is that when you train with this loss, you're actually back propagating through the synthesis basis, which you can think of as the inverse short time Fourier transform usually. One way that we've found to really improve speech enhancement systems is by adding what we call consistency projections. So the idea here is that right after you mask your input mixture STFT, you're going to project that masked STFT in a couple principled ways. And there's two particular projections, STFT consistency and mixture consistency. And I'll talk about each of these. STFTs are interesting. If you take the STFT of some signal and you element-wise multiply it with a mask, you're going to get this masked STFT. But the problem with that is that that masked STFT does not actually correspond to a real valued time domain signal. There is no real valued time domain signal that you could take the STFT of that would match up with this masked STFT. So to fix this problem, what you can do is you can just take your masked STFT, run it through an inverse STFT, and then run the STFT forward again. And that gives you a consistent STFT, which is in this blue box. To illustrate the difference between these two things, here we're plotting in the red box the error between the masked STFT and the projected consistent STFT. So you can see that there's appreciable error there. So what this is saying is if you're using a spectrogram-based loss like L2, if you are measuring it on the masked STFT that is not consistent, then you potentially have an extra source of error that is unrelated to the problem of trying to enhance signals better. So the second type of consistency transform is mixture consistency. And this is based on the assumption that your mixture signal is the linear superposition of multiple sources. So if you're making estimates of those sources, shouldn't they add up to the original mixture? So the way we implement this is within each time frequency bin of estimated sources. So you can think of this tensor on the right as a time by frequency by 2, say, because we have 2 sources here, thing. And so in each time frequency bin, we're going to take a slice of that. We're going to pretend that those time frequency bins are real valued instead of complex valued, so we can get a good visualization. And so we can plot that as this point in 2-dimensional space. In 2D space, you can draw this constraint surface in green. So all the points along that surface are mixture consistent. They are points where you add up the 2 source estimates in that time frequency bin, it equals the mixture. And what you can do is you can just project your source estimate in this time frequency bin onto the constraint surface. And then you just do this for every time frequency bin. You can also derive a little more general version of this. So let's say that you have some idea of how uncertain your source estimates are. For example, let's say you have a variance for each of them. Well, in this case, you can actually do a statistically optimal thing here by projecting just a little bit differently. And the amount that you deviate from this orthogonal projection on the constraint surface is just a function of the ratio between these 2 variances. So here I say STD to mean standard deviation. So we've tried a couple different ways of defining these variances. One way is just saying, oh, it's the magnitude squared of the estimated source time frequency bins. Another thing we've done is just have the network predict it. So we actually have the network predicting these variances for each time frequency bin for all the sources. Here are the results we get by using this. So I guess it takes a sec to process this fig, but the solid markers are where we've used STFT consistency. So that's where you take an inverse STFT and forward STFT, and then the different shape markers are different types of mixture consistency. We have both the unweighted version and the weighted version that I described, and you can see that the triangle, which is the weighted learned version, is the one that generally works best. One other thing we tried here was using either real valued or complex valued masks for the enhancement. And you can see that a complex mask performs a little bit better, a couple tenths of a dB better. The kind of main takeaway from this is that if you're using STFTs to implement source separation, just adding these 2 very simple consistency projection layers can potentially give you a gain of, at least a significant fraction of a dB in terms of output SNR. So that was consistency. A second thing we've been experimenting with lately and have actually had a lot of success with is using a different type of basis than the STFT. This is a recent paper that came out called TASNet. And instead of using a short-time Fourier transform as our analysis and synthesis bases, we're instead going to learn these bases. And the other interesting thing about this is that we're not going to use, say, 50 millisecond basis functions as used in the STFT. We're going to use really short basis functions, 2.5 milliseconds. And it turns out that this really works quite well. One other thing that changes is that instead of having that convolutional bidirectional LSTM dense network, we instead use a stacked network of dilated 1D convolutions. So we change the dilation factor at each level. This leads to a very big effective receptive field for the CNN. And I'll describe that a little more. So here is a diagram of this dilated convolution network. It's kind of inspired by the WaveNet architecture. We're just changing the dilation factor as we go up the network. Within each of these blocks, there are some residual connections, and then there's also some separable convolutions which help reduce the number of trainable parameters. Let's play some audio. So this is a pretty noisy example. It's a male with car noise in the background.
Melody.
How's the level on that? I'll play it one more time.
Melody.
So that was our STFT with LSTM, and this is TASNet. Oop, sorry.
Melody.
So you can hear the TASNet clips the speech a little less there. I want to play one more example.
Congregations of his disciples were proscribed by the imperial.
This is a really challenging scraping sound.
Congregations of his disciples were proscribed by the imperial.
So you can still kind of hear it in there.
Congregations of his disciples were proscribed by the imperial.
And TASNet pretty much knocks it out, which is pretty cool. So I only have a couple minutes left, but I wanted to share some recent work that we've been doing on not speech separation, but universal sound separation. And so the idea here is that we as humans can segregate the audio stream coming to us into a bunch of different sources. For example, phone ringing from water pouring into a glass with ice. And so what we did is we built a big database of mixtures of arbitrary sounds from a big sound effects corpus. And we trained these networks in a very similar way to our speech separation. With one twist, we used what's known as a permutation invariant loss. So when you're doing speech enhancement, it's very easy to know what the class of the different slots for your separated sources are, right? You have the speech output and the noise output. But when you're separating arbitrary sounds, there's no real good way to assign the separated sources to a class. So what you do instead is use this permutation invariant loss. So you're basically trying to align the reference sources to your estimated sources. And so these are the results we have so far. One very interesting thing to see from this slide is that the optimal window size for separating arbitrary sounds compared to doing speech enhancement are very different. So for speech enhancement, you can see that if we use an oracle method, this red line, it actually peaks around 50 milliseconds or so. That's the plot on the left. But for these arbitrary separations, you can see that the peaks in these red curves is more around like 10 milliseconds. Furthermore, we've also seen that using a STFT with the TASNet masking architecture can work a little bit better than the learned basis with the TASNet masking architecture. So this is a work in progress, but we should hopefully have a paper out on it soon. And so just for fun, I want to play you a few audio clips from this new universal sound separation model. So refreshing. And one more. I like this one. So you can hear in that last one, there's a little bit of kind of ducking out in time on the shaving foam separation. But you know, generally this model has been working pretty well. So we're actively working on analyzing the cases where this works well and where it doesn't work well. But we're pretty excited to get these initial results. So I'm sorry, I think I've used up a little more time than I should have, but thank you very much, and I'm happy to. Okay, great.
Thank you for the talk. The ducking or pumping that I've heard could have been related to the low frequency resolution for your very small window size for basis functions. And I'm wondering if you have tried something like multi-resolution where we can use different FFT sizes in parallel and join results.
Yeah, I think that's a really good idea. It's something we've thought about doing, and I think we'll definitely give it a try. I think it's a good intuition.
Maybe one more quick question. Cool. Thank you so much.
Thank you.
So the next speaker is Zhou. He is working in Dolby Laboratories in San Francisco, currently creating technologies for speech and audio using deep learning. His recent work includes work on human analytics, audio coding, and voice conversion. He'll be presenting his recent work on high-quality speech, which has been accepted at ICASP. Thank you. Oh, yeah. Oh, I'm going to start introducing audio coding and then hand it over to Zhou. I was supposed to do this. So describing what we do in audio coding is always challenging. But last month, I saw a presentation by Annie, director of video algorithms at Netflix, who used an analogy to describe video coding, which I'm going to borrow as well. I just do mics and speak in stereo. Thank you. So hopefully some of you are familiar with who she is. Marie Kondo. She is the author of Life-Changing Magic of Tidying Up. And if you're not into books, she currently has a show on Netflix. If you don't watch content, she is on social media. She seems to be everywhere. And the approach she uses for decluttering is basically take everything you have, go over item by item, touch it, bring it close to you, and see if it gives you joy. For everything which gives you joy, you keep. And everything which does not give you joy, you throw away. And when you have discarded most of your possessions, you go and pack it into small, neat boxes. And she has a really good method of packing where everything from shirts to pants to every clothing you have can be packed in small, square, or square boxes. And I believe that we do something similar in audio coding. When we want to compress, we take a speech and discard whatever does not carry a lot of information, and then we pack it pretty well. And on the decoding side, what we do is the reverse. We unpack it and try to resynthesize speech. And that is something we have been doing for decades. But the big challenge which comes here is once you really start getting at a low bit rate, you start discarding a lot of information. And when you discard a lot of information, resynthesizing speech at high quality becomes really, really challenging. But now, with deep learning, we have powerful generative models, which even with limited information are able to synthesize speech at a high quality. So I'm going to hand it over to Zhou, who's going to give you the technical details.
Okay, thanks, Vivek. All right, it's an honor to be here. So this work is some of the recent work we've did in speech compression, and this work is a collaboration with our Dolby Stockholm team. As mentioned in Vivek's introduction talk, these waveform generative models really push the recent advancement of deep learning in audio. So these sequential generative models directly estimate the waveform distribution, and they factorize the joint distribution into the product of each audio sample into the product of individual audio sample distribution conditioned on all the previous sample history. Just to name a few of these generative models. So one is WaveNet, based on dilated convolution, and we have SampleRNN based on a hierarchy of recurrent nets, and we also have WaveRNN, really focuses on low complexity and having recurrent nets running on every sample. In our work, we use the SampleRNN as the main generative model. So next, let me introduce a little bit more about SampleRNN. It was introduced by Soros Mary et al. From Montreal Institute of Learning Algorithm. The model itself consists of a stack of recurrent layers running on different temporal resolution, and MLP, multi-layer perception, running on every sample level. So therefore, there are these hierarchy tiers in this architecture. The diagram is an unloaded version of a 3-tier SampleRNN. So the circles here are the recurrent layers, and the box down here are the MLP layers. So the uniqueness is that each tier runs on a different temporal resolution. For example, the frame size of tier 3 is 16 here. So tier 3 actually runs for every 16 samples. And tier 2 runs on frame size of 4, and tier 1 always running on every sample because it does the main sample distribution prediction. So in our work, we particularly used a 4-tier configuration of SampleRNN. One thing to note is that without conditioning, SampleRNN only babbles. So we need to provide additional conditioning information to make SampleRNN generate intelligible speech. And so here we have a conditioning information HT, and it's being handled by a couple of 1-by-1 convolution, and then each tier gets its own 1-by-1 convolution, and then it's being added to the sample history conditioning before the recurrent nets. So therefore, when the model doing the prediction, it's actually conditioned on both sample history as well as the additional conditioning information. So to train this conditional information, how do we do that? We have a speech running on 16 kilohertz, and then we use a vocoder extractor to extract vocoder features such as LPC filter, the IMS levels of the LPC residual, pitch, and then also the voicing level. So these features are used as conditioning information for SampleRNN to predict the distribution of audio samples. And then in training, the overall system is optimized through minimizing the negative log likelihood. And once we have this conditional SampleRNN, let me introduce how we fit this into a coding scheme. So it's pretty natural that let SampleRNN be in the decoder side, because it does the speech reconstruction. The slightly different thing is that the SampleRNN here is actually trained with the quantized vocoder features. So the whole coding scheme looks like this. So we first do the same thing, extract features, vocoder features, and then these vocoder features are being quantized. After quantization, we do entropy coding, and then we get bitstream. On the decoder side, we do entropy decoding, and then finally, SampleRNN reconstructed the speech conditioned on quantized features. So we evaluate our coding scheme based on a Marshall listening test. For people not familiar with the Marshall test, a score between 80 to 100 is considered as excellent quality. So we have 3 coding systems here. One is AMAR wideband at 23 kilobits per second. And then we have Silk at 16 kilobits per second, which we consider it as the state-of-the-art speech codec. And we have our system running at 6.4 kilobits per second. So as we can see, we achieve excellent quality at 2.5x lower bitrate than the state-of-the-art codecs. The main reason we include AMAR wideband here is that the quality of AMAR wideband has not been exceeded by other deep learning based low bitrate coding scheme. So it actually allows us to compare results with other proposed scheme. And next, let's play some audio, listen to the demo files. The first, I'm gonna play the reference file.
The 100 share index closed 3.1 points higher at 1,840.8.
And then AMAR wideband on 23 kilobits per second.
The 100 share index closed 3.1 points higher at 1,840.8.
Silk 16.
The 100 share index closed 3.1 points higher at 1,840.8.
Our system at 6.4.
The 100 share index closed 3.1 points higher at 1,840.8.
It's less audible in this room, but if we put on headphones, it's pretty obvious, I promise. This is a pretty impressive, and but it's just a coding prototype. Why I'm saying that? Because the system is trained for clean speech, and it works very well for clean speech with a relative high complexity, but it's not robust to either simultaneously talkers or background noise, background music. So some of the main research directions including improve the robustness. So the system needs to be able to handle different situations, such as like simultaneously talkers or different backgrounds. And also it needs to be running on low complexity. The system needs to be able to run in real time. Just point out some recent related work. As you can see, there are lots of research activities, efforts are happening. Every few months, there are new architectures, new papers being published. They're pushing for low bitrate, low complexity. You can see some of the work has already achieved real time. So it's a really amazing and exciting field. I can't wait to see more. That concludes my presentation, and thank you for your time. Ready for questions?
So questions.
Thank you for the talk. It's also a very good idea. I would like to if you give me your opinion on this stuff. I mean, SampleRNN and WaveNet are very good to generate samples, high quality, impressive, right. But are very, very slow. So do you really see a way to make this working in real time, or
yes. There are lots of optimization work going on. Like WaveRNN is actually, I think they are able to run in like CPU real time. And then there is recent work from, I think also from Mozilla and Google. They proposed a WaveRNN based LPCnet that's being able to like running on real time on CPU, mobile CPU. So definitely there are like research work going on in this direction.
Thank you.
Yep. Thanks.
Any other questions?
Yes, thank you. So I don't understand much about the synthesis system you're using, but I'm thinking it must have a kernel waveforms that it used in the synthesis problem. So can you talk about that? Because you begin with the LPC, and I understand the synthesis part of that, and now you're replacing that and getting good results. So maybe talk a little bit about how this network ends up doing the synthesis.
The network is actually predicting the sample distribution, and then it's actually done it like in an autoregressive way. So once we have the sample distribution, it draws a sample, like a waveform sample from this distribution, and then as a feedback to the history, like autoregressive way.
Any other questions? Cool. Thank you, Zhou. Thank you. So for our last speaker today, we have Vincent Lostanlen. He is a postdoctoral researcher affiliated to the Cornell Lab of Ornithology and is currently working both at the MARL and the NYU Center for Urban Science and Progress. His research lies in the intersection between time frequency analysis and deep learning with applications in music similarity retrieval, ecoacoustic monitoring, and computer music. He'll be talking about BirdVox machine learning for bird migratory monitoring. Thank you.
Thank you. Good evening, everyone. Hi. Thank you, Vivek. My dear colleagues, for us in New York, and pretty much everyone around our latitudes, the month of April brings a very special symphony. Every night, if you lend your ears to the sky, you will notice a distant, steady flow of birds chirping above you. The beautiful images you're seeing, filmed by Susan Reinert for her documentary The Messenger illustrates this nocturnal flight in slow motion. Birds evolved in a world where they are primarily migrating at night, oriented by the magnetic field as well as the apparent rotation of stars. But with the industrialization of our societies, this admirable skill is now put under great jeopardy. Because birds get trapped into beams of light, such as this one, which is the tribute in light, a commemoration of 9/11, yearly commemoration. They get trapped and no longer have a chance to find the Northern Star. This man is my colleague Andrew Farnsworth, a researcher at the Cornell Lab of Ornithology. He's seen studying the tribute in light here. In partnership with tribute organizers, he showed that shutting down the lights for only 20 minutes at a time was sufficient to disperse the flock of birds that get trapped into the beams. So even though this is a considerable problem, it's not completely hopeless. But the problem is, ground zero is only one of the thousands of hazardous sites for migratory birds in North America. So how to devise a principled research policy to protect biodiversity at the continental scale? There's already a number of options to address that issue, and the most scalable option at the moment is to use radar monitoring. So every green point in the map that you see here is a weather surveillance radar station, and just like you can locate the motion of clouds throughout the day, you can also locate the motion of bird flocks throughout the night. So here, this is the date for yesterday, so that's April 23rd at 8 p.m. Eastern Time. And now if I play this, you see the red vertical stripe of sunset and then followed by sunrise. And we see these birds migrating at night in between sunset and sunrise. So these were the two previous nights. And this is, you can check these maps every day on birdcast.info. And this is obtained just by radar, which is quite amazing. You know, birds really see the sunset on the west, and they leave that sunset on their left wing, and they know that they have to migrate north. So that's why many of them migrate at night. But there's one part missing from this story. One very important shortcoming of radar imagery is that here there's no species. There's no species information. So we'd like to complement that radar imagery with acoustic monitoring. Oh, and by the way, Birdcast also has forecast for the next day. So this is forecast for tonight. This is the forecast for tomorrow. And this is the forecast for Saturday. So it's going to be a good weekend for birding in Louisiana and Texas. So all of that is great, but again, there's no species in what we see here. The other option is to rely on the countless bird watchers on the field who collectively have provided over 30 million checklists to the eBird app. And so with colleagues at Cornell, we've put together this animation and visualization of habitat maps, which have an incredible spatial resolution and are extremely helpful for finding the species-wise habitat on a month-to-month basis. But here, the caveat is that this is, of course, there's a lag of several days between a given species landing on a site and bird watchers actually checking in that list into our system. So here we are faced with a conundrum. If every species follows a different migration route and is exposed to different human threats, how can we protect it at a continental scale with not only radar and not only crowdsourced information? The difficult answer that I intend to provide tonight is to use sound. So this person is Bill Evans from the NGO Old Bird. It's based in Ithaca, New York. And so what he did was he made an assembly guide for building your own acoustic monitoring station for these flight calls. So here's the assembly guide from Bill. You just solder these components onto a board. You pinch a hole through a dinner plate. You tape it with plastic so that it's waterproof. You do this hole in this plastic bucket, you attach everything at the bottom of a flower pot, so as you can see, it's very low cost and very easy to make. And then you fasten safely that flower pot onto your roof, and there you go. You have a DIY acoustic monitoring station. And it's called an autonomous recording unit, which is a bit of a misnomer because it's autonomous in the sense that you don't require a human operator for audio acquisition, but you still need a human operator for data pinpointing, labeling, and counting, and that's a Sisyphean task. So, luckily, Andrew Farnsworth, my colleague from Cornell, and whom you saw with the binoculars, put together this very compelling associative table from flight call in the time frequency domain to species. So here we really see that every species has a distinct acoustic signature with subtle yet systematic variations in trill extent, modulation rate, and so on. So the good news is that even though learning this and muscle memorizing this would take many years, possibly decades, and there's a handful of people who are able to do that, to map flight call to species with perfect accuracy, this is exactly the sort of pattern recognition techniques in the time frequency domain that are within reach of modern deep learning techniques. So we started our journey with BirdVox by simply reproducing the algorithm for automatic detection of flight calls that Bill had put together in the 90s. So that algorithm, and all the algorithms I'm going to present today, are measured on a precision versus recall diagram. So recall means how many relevant items are retrieved, and precision means how many retrieved items are relevant. So it's a trade-off in terms of threshold. So the old bird detector, which really uses very little machine learning, as you can see here from the code, has terrible both precision and recall. It's about 10% in both. So that means that not only are we missing or failing to detect 90% of the flight calls in a given full night, but also what old bird retrieves is 90% irrelevant to the problem of monitoring flight calls. So in a way, it's heartwarming. It means that we have huge space for improvement. So then we thought, okay, maybe now that we have Andrew Farnsworth, who did the thankless task of annotating 60 hours of data, we can train a machine learning model. So our model relies on a unsupervised learning stage, which is spherical k-means, SKM, followed by a supervised binary classification stage, in this case, SVM, support vector machine. So very classical, traditional, so to speak, shallow learning technique. So that was actually marginally below old bird, which means that feature engineering is not always the worst possible baseline. But thankfully, this machine learning model allowed us to put us off the ground, so to speak, in the sense that we could use the false alarms of this model to produce challenging negatives for an upcoming data set. And so we just ranked the false alarms by decreasing confidence and took 300,000 confounding factors. In other words, audio clips that would fool the shallow learning detector. And then we started training a deep learning classifier, binary classifier. So this is the deep learning classifier I presented at ICASP. It's a very conventional convolutional neural network. It's about the same sort of architecture as the one we use for environmental sound classification. Only the parameters for time frequency representation here differ a lot, but that's besides the point. So that brought us to 50% precision and 50% recall. So huge improvement. It's a drastic improvement. 50% precision, 50% recall means that we retrieve half of what's in there, and what we retrieve is half relevant. And luckily, this can be written with not a lot of code. Then we thought maybe the model would benefit from even a greater amount of diversity in the data. So we applied randomized perturbations, randomized digital audio effects, such as time, as you can see, frequency transposition, time stretching, addition of background noise, and dynamic range compression. And that scaled up our data set of 300,000 calls to, or 300,000 clips to 10 million clips. And data augmentation alone bumped the area under the precision recall curve to 60%. So the great thing about this is that this comes at zero prediction cost, computational cost. It's really the same model, it's just trained on more data. So it comes essentially for free. And then that was the baseline that was difficult to beat. Because thus far we've just followed the traditional, iterations of a classification problem. You start with features, then you use traditional machine learning, and then deep learning, and then you augment. Okay, nothing new under the sun. But there is a very peculiar aspect of flight call monitoring that is not present in usual speech applications or music applications. It's non-stationarity of background noise. This is a full night recording from our data set. So this has been thoroughly annotated by Andrew Farnsworth at the millisecond scale and with species. So that's 11 hours of audio from dusk to dawn. And so here you can't see any flight calls because the zoom out is so large that, and the flight calls are so short that we don't see them on the display. But what we see, and what's really interesting to note, is non-stationarity at a 2-hour scale or 30-minute scale. So what we notice here, for instance, we notice a passing train around 8 p.m. We notice some insects in that 2.5 kilohertz frequency range. We have reduced car traffic at night, and finally, some thrushes. That's the dawn chorus. So the question that arises here is, how do we adapt to this form of non-stationarity? How do we make it so that a deep neural network that would be trained on, let's say, dawn recording conditions would not fail at dusk, and vice versa? So we took inspiration from this paper, which was developed for initial applications of far-field keyword spotting in the smart home. And so what these authors had come with is a trainable acoustic front end. So it's a drop-in replacement of logarithmic compression for your favorite time frequency representation, be it STFT or MEL spectrogram or CQT or whatever. It doesn't affect the time frequency axes, it does affect the magnitude scaling. And so what was needed to do was to rethink this model, and so formally analyze this model so that we could adjust its hyperparameters from keyword spotting in the smart home to outdoor far-field flight call monitoring. So that's what I did, and I showed that it was that PCEN, this method, stationarizes, Gaussianizes, and whitens background noise under mild theoretical conditions. So that brought us at 60% area under the precision recall curve. And then the last thing that we noted, aside from non-stationarity, is non-uniformity. So from one station to another in the vicinity of Ithaca, New York, we have tremendous variations in average noise or quantiles of power spectral density. So we thought, okay, there is a need to adapt for these variations in recording conditions. But if that is true for Tompkins County, New York, imagine how dire the problem becomes when you scale this area by a factor of 1 million or so, and we have the ambition of having a single model for the whole continent. So what we did was relatively straightforward. We took these quantile summary statistics of PCEN spectrogram, and we supplied a deep convolutional neural network with these so-called auxiliary features. And so although these auxiliary features don't tell us anything about the class, they do help learning a form of bias at the last layer that ultimately can be reinterpreted post hoc as an adaptive threshold, because these auxiliary features change very slowly, and of course the transformation here is continuous. So we have also very slow variations of this adaptive bias. So by reordering the terms, we really see that it's the detection criterion amounts to an adaptive threshold. And that adaptive threshold brought state-of-the-art results at 76% accuracy, area under the precision recall curve. So that model is called BirdVox Detect. And people can download it. We've partnered with Bill Evans as well as other people so that bird watchers and ornithologists can just run it on their data and get some flight call counts. So then the next question would be, how do we get species? So we have some plans for that, of course, and we are already seeing some good results in species classification. And the last question would be, how do we obtain reliable count? You know, how good is a model that's 76% area under the curve? Is that usable at all? And it seems like yes. It seems like from the next BirdVox annotation campaign, we've had most of our nights being within a factor 2 or within a factor 5 of the true flight call count. So even though we have some false alarms, even though we have some misdetections, these ultimately compensate quite well. And so our counts and species compositions are relatively satisfying. So that will be the next iteration. I want to end this talk with an invitation. On October 25 and 26, I will be chairing an international workshop on detection and classification of acoustic scenes and events, or DKs. So this has published proceedings, it has 5 data science challenges, and it has some meet and greet time. So whether you are a machine learning hotshot wanting to get a crack at one of these challenges, whether you want to submit your research to the scrutiny of our peer review, or whether you just want to meet some interesting people, you are always welcome at NYU Tandon. In the meantime, I beg you, keep your cat indoors. I guess keep your cat indoors, turn off your lights at night, and keep your head up. Thank you.
Thank you for the amazing talk. Questions? No questions. There have to be.
So the talk is all about, given the acoustic signal, what does it mean in terms of your flight count?
Yes.
Is it hard or easy? You showed the detector on the roof. Is that part of the problem easy, or is there a need for more pervasive arrays of sensors if you got your, assuming your research problem is like, hey, if I just had lots of microphones, I would know a lot more. How much does the do-it-yourself, what did you call it in the beginning of the talk?
Yeah, do-it-yourself, yes.
How much is that a part of the bigger problem of continental migration monitoring?
Yeah, so hardware is important in audio all across the board. I won't debate that. And we are facing an issue of scalability here. We are using and advocating do-it-yourself microphones simply because that's what we can afford. And I think it's right to do it that way. The bird watching community has lived with this DIY spirit, and I think we should embrace that. That said, regarding the question of deployment at the continental scale, I think you make a very good point in that we don't aim at a full coverage of the whole continent. That's not at all what we mean. Radar has much better spatial resolution than acoustic monitoring, and we're okay with that, because what we want is a species distribution that is better than radar and that is finer in time than crowdsourcing. So we're sitting in between those two scales of time and space.
So just follow up with a comment. When you think about Internet of Things and stoplight video cameras, and you think, well, what would I do with a microphone on the street? Usually it's very ominous and dark. But your problem makes it really sunny and cheery, and maybe there's hope for the idea that audio, Internet of Things might have applications that are all good and upside, as opposed to, tracking where someone walks, which is kind of a dark scenario.
Yeah.
Right? So I'm looking for the upside in what you're saying. So Good.
Good. Yeah, absolutely.
Thank you so much for the optimistic perspective. More questions?
So you mentioned like trying to have a single model for like the whole continent. Based on sort of just the volume of the data you can collect and sort of the diversity of I imagine there's some diversity of the bird species that are distributed across the continent as well. Like how many, like what, I guess the way I would approach it is how necessary is it to have a single model for the whole continent versus just making it easier to retrain new models, especially because you can imagine that a model that's based in the East Coast will not see, I mean, I don't actually know enough about birds to say this.
No, but you're right, you're right. Yeah.
Will not see certain
East
species
Coast, West
that
Coast
are West
are
Coast.
different migration routes.
Yeah. So
I'll grant you this, yes.
Right. So having a single model based on all the data for the whole continent, I may have misunderstood this. Is that necessary?
Is the bias versus variance trade-off necessary?
I suppose that's part of it, yeah.
Voilà. That's it. It's a bias versus variance trade-off.
Okay.
Is it necessary to have that trade-off? No, but you know, the more data you can afford, the better the fit and the less the overfitting. Then you make a strong point about the fact that there is not independence between species and location. So that's absolutely true. But that has little to do with the question of detecting for presence.
Okay, yeah, for presence.
Yes, so we're really working in a two-tier approach here, where we have a detector first, and then we have a classifier downstream, which, yes, you're completely right, does have a spatial temporal prior, which is obtained by crowdsourced information, yes.
Any more questions? Thank you so much for that amazing presentation. And thank you all for coming. It's been an exciting day to me. I learned a lot. And to me, it's very exciting about the amount of research going, and I'm pretty optimistic that we will be able to change the future.